In the last few videos, we introduced the control volume analysis to look at conservation of mass for fluid in motion. And control volume analysis really forms the backbone of our ability to analyze fluids in motion. And we use it for basically any type of engineering problem that especially involves fluids or involves heat or energy transfer, such as in thermodynamics. So you just need to remember that control volume analysis really provides you a way to break down the problem and analyze it and get an engineering solution. Okay? So if we're talking about fluids in motion, the next logical step would be to look at conservation of momentum. And conservation of momentum is very important from an engineering perspective because we're often interested in the forces that are involved in the moving fluids. We either want to put energy and force into the system through a pump, or we want to extract energy through the forces out of the system, like in a hydroelectric plant. Or, for example, if we're designing a tall building, we need to design that building so that it can withstand the force of the wind on the building structure itself. However, before we get into the control volume analysis of conservation of momentum, we need to consider all the forces that come into play when we're going to build that balance. And the first one I'd like to talk about, because we already are familiar with pressure, we're going to talk about pressure variation in fluids in motion. Recall from your hydrostatics class that pressure is very important. It's equal to the specific weight of the fluid times the amount of fluid above it. So it's basically the weight of the fluid above the point that you're looking at. And it gives us a force when we multiply it by the area. And so we need to look at how that's going to ultimately be incorporated into our momentum equation. But before we get into the nuts and bolts of that, I want to give you a couple examples of why we're so interested in pressure and how pressure really generates force. And two really clear examples that you already have a very intuitive sense of are a sailboat moving on water and the force of a wind on a building. If you've ever been in a sailboat, the wind blows, there's a pressure difference that comes up between the point here, P1, that is behind the sail, and P2, and P1 is greater than P2. We multiply that by the area of the sail, and we get a force in that direction, and consequently, the boat moves. Okay? Similarly, if we build a skyscraper, you may have been in a tall skyscraper on a windy day, and you can actually feel the building moving a little bit. And that's the same thing. We have P1 here and P2 here. P1 is greater than P2, so there's a difference in pressure across that obstacle, which leads to a force, because without the wind, the pressure would be the same on both sides, and so you have no force. So it's really that difference in force, and remember that as we move through this lecture. And so again, we get a force moving in this direction, and we have to design the building so that that force doesn't push the building over. Okay? So let's now move to a more mathematical description of where pressure comes up in our conservation of momentum and how it varies in a fluid in motion. And to do that, I want to consider a cylindrical control volume that is being accelerated in the direction S. And so I have the S direction aligned with the center of the cylinder there. I've defined the length of that cylinder as delta S. The area of the ends of the cylinder is delta A, and that's not going to change from one end to the other. And then I have a normal direction S hat, which is at an angle alpha to our normal Cartesian coordinate system of X and Z. Okay? So the first thing we need to do is define the forces on the system. And the first one that we know is going to act right here. It's going to be in a downward, and that's going to be our weight. So there's the weight of the fluid acting at the centroid, acting downwards. The next two forces in this system, we're going to have a pressure at this face, so we'll have that pressure here. So that's going to be P times delta A, because we need to multiply the area by the area there to get a force. And then we're going to have a similar force acting on the other face here. And if we use our Taylor series expansion from before, this is going to be P plus delta, or sorry, dp, let me erase that real quick. dp over ds times delta s, oops, sorry. The delta s goes in the parentheses, delta s, delta a. So that's just a straightforward Taylor series expansion where we're saying that the pressure at the other end cap is the gradient in pressure along that direction times the distance we've traveled, and then we have the area to convert it to a force. And then we can finally define W is equal to gamma V, or the specific weight, times delta A, delta S, right? So the next thing we want to do is just look at the sum of the forces in the S direction, okay? So what we're going to do is we're going to say, oops, we're going to look at the sum of the forces in the S direction, and instead of setting that equal to 0 like we do in statics, we're told that the cylinder is being accelerated in the direction S. And so that force is going to be equal to mass times the acceleration in the S direction. Okay? So it's just Newton's second law. Okay? So now we want to put the forces that we described in the figure into this sum of the forces. So let's write that out. We have P delta A, that's the force, pressure force on the first face of the cylinder. It's acting in the positive S direction. Then we're going to have minus, parentheses, P plus dP over ds delta S delta A. So that's the pressure acting on the other end of the cylinder. And one thing I should mention at this point, since we're adding the pressures up, is that there's also pressure around the outside of the cylinder, but that doesn't actually act in the S direction at all. It's always going to be in a plane that's not along X, it's perpendicular, so it doesn't show up. But also, if we did sum the pressures around that cylinder, they're going to add up to 0. Okay? And then finally we have the weight of the fluids. We have minus gamma delta A delta S. However, we're only concerned about the S direction, and so it's not that full. We have to use some trigonometry and to get, and this is going to be the sine times the sine of alpha to get that component in the S direction, okay? And that's going to be equal to rho delta, oh, I'm sorry, erase that. That's going to be equal to the mass, which is going to be rho times delta A delta S times the acceleration in the S direction. Okay, rho delta A delta S. So that's just the density times the volume. Okay? So the first thing that we're going to see here is that in all of these types of problems, the first two terms are going to cancel. So if we look at this, P delta A, and if we multiplied this second term out, this here, if we multiplied this one out, the first part of it here is going to be negative P delta A, so those are going to cancel. So get rid of those. And so we really only care about the pressure difference. And remember, that's what I talked about in the intro when we talked about the difference in pressure across a sail or across the building. Okay? So now let's rewrite that again. So now that we can cancel those terms, we can say that negative dP over ds delta S delta A minus gamma delta A delta S sine alpha is equal to rho delta A delta S A S. Okay? Now the next thing we see that's pretty obvious is that every single term in here has the delta A delta S. So we can get rid of all that. So let's do that. And then we can write it out again. So we now have negative dp over ds minus gamma sine alpha is equal to rho as acceleration in s direction. And this is equation 3.4 in your book, okay? But I want to take this a little bit further. So let's now look at the angle alpha. Let's look at alpha, okay? So let's draw this out. So if we look at the angle alpha, we're going to have something that looks like this. And this is the angle alpha here. And here along this length we have delta s, and this is going to be delta z, right? So from trigonometry we can say that delta z over delta s is equal to the sine of alpha, okay? And if we look at the limit as delta s goes to 0, so now we're going to take that limit, we're going to shrink the delta s along that s direction to something infinitely small. We get that dz over ds is equal to the sine of alpha. And we can substitute that into our equation. So let's do that over here. So now we can substitute that in. I'm going to flip the way I've written it, but it's going to be rho as. So the density times the acceleration in the s direction is going to equal to negative dp over ds minus gamma, and this is where we'll plug in our new expression for the sine of alpha, dz over ds. Okay? So now the next thing we can do is assume that the gamma, the specific weight of the fluid for this case, is going to be constant, and then we can group these together. And we can write it again. So rho as is equal to negative d over ds times p plus gamma z. And this is Euler's equation, named for the person who discovered it. Same Euler that developed our coordinate system that we often use in the perspective of looking at fluid mechanics, where we have a grid and we look at one particular point and see how the velocity evolves at that point through time. So that's the same person. And then the reason that we wanted to go through this, not only just to get to Euler's equation, which is a famous equation that we use in fluid mechanics, let's look at the case where there's no acceleration. So let's say, so this is as equals 0, and this is a special case. And you'll see why we're interested in this in a minute. If there's no acceleration, then we can say that d over ds of p plus gamma z is equal to 0, right? So we get rid of the negative sign because it doesn't matter. We just know that this is equal to 0. That's pretty easy to integrate, so let's integrate that with respect to s. And we're going to get p plus gamma z is equal to a constant. So that's a constant, right? And now take the derivative in the z direction. Okay, so the derivative of p in the z direction is going to be dp over dz, right? The derivative of the gamma z in the z direction would be gamma. And then the derivative, of the constant in the z direction is going to be 0. So we can now move the gamma to the other side, and we get dp dz equals negative gamma. And that should look very familiar. If we move the dz over now and integrate it, we get p equals gamma z, which is the rho gh. It's hydrostatics. So we can, by setting the acceleration equal to 0 and basically saying that there's no motion in the fluid, we recover our equation that we used in hydrostatics to analyze. So that's how pressure varies with fluids and motions. And again, we're interested often in the pressure difference between 2 points and not so much the absolute pressure. All right, in the next video or two, we'll look at a couple of examples of applying Euler's equation to some engineering problems.